Okay, now we're going to talk about angular acceleration. That's the third descriptor we had. And again, we're just adding angular so that it is for the rotational motion. We are going to use what we learned before. And first of all, we can define both average and instantaneous acceleration, just like we did with the linear motion. And average angular acceleration, I'm just going to write down what we use for this one. For linear case, we used little a, right? And a vector, and we put a bar because it was the average acceleration, and that was equal to change in velocity divided by change in time. So again, average means is for over a finite time, and instantaneous one was again a, and it's a vector, and then we took the limit and we got dv over dt. Right, so what we are doing here is we are using, instead of a, we are using alpha. Okay, this chapter is all about Greek letters. So we are using angular acceleration is alpha, so a goes to alpha, so there's some sort of a mapping. So far, let's recall what we did. We said like, I'm just going to call x for one dimension, x goes to theta, okay, and v goes to omega, and now a goes to alpha. So if you look at the equation that we derived for the linear motion, these ones, now change those, use these new letters. They are the same equations, okay? There's very similar concepts. Again, of course, the units are different. So if you look at the units on this one, since alpha is delta omega over delta t, if you remember, omega was radians per second, so divided by another second will give you radians per second square. Okay, so instead of meters per second square, you have radians per second square. Okay, so next is a supplemental example. Please try to go over this. Again, we don't cover these in class, but it's a quick one too. But they're good practices before moving on to the activity. Just check your understanding if you can do it. These are quiz questions. I'm going to, what am I doing? I'm gonna move on. So we're gonna get to the constant angular acceleration. Okay, so do you kind of realize what we're gonna do? Constant acceleration, right? But it is angular. So we're gonna develop the similar equations as we've seen in the linear motion. So we're looking at a special case. Why is it special? Because we're saying that acceleration is constant, okay? And first, let's take a moment to review how we found the linear motion equations for constant acceleration. So we're going to do a quick review on those, chapter 2 and 4 as well. So we know the linear motion, velocity is the position, derivative of position with respect to time, right? dx over dt. And we also know that acceleration is the derivative of the velocity relative with respect to time. And using these two equations and starting with the acceleration equation, as you can see here, we multiply both sides by dt, but we want v, not dv. So we don't want the infinitesimally small velocity, we want the velocity itself. How do we undo the differential? We use an integral, right? So we've done this already. I'm gonna go quickly. Take the integral of both sides, and then knowing that acceleration is constant, take it out of the integral, and that's what you get, right? And now the solution to that dv integral is v, and dt integral gives you t, but there's also a, and then both integrals will give you integration constant. You can combine them as one, which is c here. And using the boundary conditions, you know that t is equal to 0, v is equal to v0, and that constant is related to the initial velocity, as we discussed again before. So you're finding that using the boundary conditions, and then changing the constant to v0, rearranging the equation gives you the velocity equation. Again, we did it in chapter 2, and then later we did it in chapter 4 as well. And then we find the position equation. To find the position equation, we use the definition v is equal to dx over dt, okay? So we're gonna get that x from here, so which means let's multiply by dt again, and also substitute what v is. V is v0 over v0 plus at, and now focus on the right side here and rearrange dx, right? And then distribute this dt on each. That's what you get. Once again, we need to integrate every term. Now we have 3 terms, and we get 3 integrals from here to there. So let's see which ones are constants. Initial velocity is constant, take it out of the integral. Acceleration is constant, take it out of the integral. Okay, and then using a bunch of integral definitions, or really they're all simple integrals. Dx integral is going to give you x, dt is going to give you t, and t to the n dt is t to the n plus 1 over n plus 1. And this is related to that. Look at what is the power of t in this case? It's simply 1, right? So n becomes 1, then this becomes t to the t squared over 2. And that gives you 1/2 t squared, and you have a, so 1/2 at squared. That's the term. And dt integral is simply t. That gives you v0 times t. And we still have an integration constant coming from all those 3 integrals. You can combine them as one and then use a boundary condition to solve. So we are plugging those in to figure out what the integration constant is, which is initial position. And then putting all together, and that gave us the position equation. And remember that when we did solve problems, we used the step-by-step process. We started with the position equation and the velocity equation. That was step 1. Step 2 was writing what is given at the start, what is given at the end. And step 3 was plugging in and solving for the unknowns. So these are the linear cases. Now we're going to do very similar things. Okay, remember we start with the acceleration equation, and we also use the velocity equation after that. Again, this is exactly the same thing, but once more, alpha is a, omega is v, and theta is x. Okay, so I'm gonna go over this real quick. Just doing that will give you the equations. Okay, so we have the velocity equation. Let's see where we have that. Okay, we have that theta and velocity is up here, right there. So this is our velocity equation, right? Angular velocity though. And this is our angular position equation. Okay, so the PDF format of this is given. You can take notes and try to do it your own, and as a good practice. So this is our angular velocity. Once you get that using the second equation, omega is d theta over dt, then you can get this bottom equation here, and this is the angular position. Okay, so again, these are very similar to what we did before in linear motion. If you do the mapping, you will get that you can just switch the letters and you will get those equations, because that's really basically what it is. So using that mapping and looking at the summary, now we have more equations, but it looks like there are much more equations now, but they're really the same thing. Okay, they're just different letters. So try to understanding the mapping first, and then try to write those equations in angular form. For example, delta x is equal to x2 minus x1. Let x go to theta, you're gonna get this equation here. Okay, so it is true for all of them. Take a look at those. Okay, and again, this part is very important, because this is how we're going to solve constant acceleration of motion, but it's going to be angular acceleration this time. Just like we did with the linear motion, these are the ones that we use. Now we're going to use these equations, and you'll see how we're going to practice them.